We'll start, sir, within 2 minutes. Since yesterday it's raining a lot, so sometimes the internet problem comes. So let's wait for 2 more minutes.
So people are still joining at a pretty good pace.
Yes, sir. Yes, sir. YouTube streaming is also started.
शेलर सर यूट्यूब लिंक भेजा है क्या आपने?
Yes, madam. Should I put it in here chat as well?
No, I'm opening it on the other device only.
Okay, I'll share it, ma'am. So, madam, you keep a watch on YouTube question answer. At
Yes,
the end,
yes,
we'll
sir.
take those as well.
Yes, sir, I'll do that. That's why I'm
Okay.
keeping it open in my
Yeah.
other device.
It's shared.
Yeah, I got it.
Yeah. Mark, sir, should I start?
Just wait for one or 2 more minutes. Let all the participants join.
Okay. By 3:05, I think we'll start.
Yes, that will be nice.
Yeah. I think we'll start now. Mark, sir, can I start? Mark, sir, am I audible to you? I think Mark, sir, is on mute. Sir, we are unable to hear you. Yeah.
I'm ready when you guys are. Can you hear me now?
Yeah.
Yeah. I'm ready when you guys are.
So welcome to all of you. On behalf of AISSMS Institute of Information Technology, I would like to extend warm welcome to our today's speaker, Mark McGranaghan, sir. Topic for today's webinar is priorities for power quality research in the integrated grid. I also welcome all the delegates who have joined today's session. Let me start with our campus. As you can see, this is our campus, All India Sri Shivaji Memorial Society. which is a premier heritage group of institutes established in 1917. And this is our Pune campus. And its campus has right from schools to engineering colleges, pharmacy, medical, and many professional courses are being run. All of you are welcome to our campus whenever you are visiting Pune. We are very lucky that we are having a management and stalwart management, and we are being guided by Sri Shahu Chhatrapati Maharaj, who is the president of All India Sri Shivaji Memorial Society. Along with him, Sri Sambhaji Raja Chhatrapati, who is vice president of AISSMS Society. Sri Maloji Raja Chhatrapati, who is honorary secretary of AISSMS Society. And Sri Suresh Pratap Shinde, who is honorary joint secretary of AISSMS Society. Our manage always motivates us and helps us to achieve our vision to uplift the common masses by rendering value added education. So this is one of the activity by our institute to reach to all the stakeholders and help them in rendering value added education. Coming to our college, we have electrical engineering department, and in electrical engineering department, we have power quality and energy conservation cell. This cell helps in power quality training to students as well as industry. We are also conducting power quality audit through power quality and energy conservation cell for the industries. In that, we specifically conduct harmonic audit, reactive power audit, transient audit, as well as general power quality consultancy is offered through this cell. We are also doing work on energy and power quality monitoring system. And in this, we involve all the students to do the activities and electricity bill analysis. As everyone knows, in Maharashtra recently KVH billing is introduced. So we are also doing electricity bill analysis and helping the industry in the power quality problem as well as in the electricity bill optimization. Now coming to today's speaker, I am honored to introduce to you today's speaker, Mark McGranaghan sir, who is the Vice President of Innovation of Electrical Power Research Institute, EPRI, from USA. He is also a IEEE fellow, and everyone knows that everyone who learns power quality, this is the first book which everyone reads, and I am very happy that I also started my power quality career by starting reading this book. So sir is the famous author of this book, Electric Power Systems Quality. Of course, sir will be, I will request sir to give his background when she start the session so that every member will know what kind of work he is doing. Before starting the session, I would like to give some general instructions. All the participants, please mute your audio. Also stop video if it is on. This will help in the saving the bandwidth. For the best results, please use headphones. If anyone wants to ask question directly to the speaker, please click on the raise button. We will unmute you during question and answer session. For YouTube participants, you can write your questions in the chat section. We will take those as well. Alternatively, in WebEx also, you can post your questions in question and answer session. Please do not post question in general chat. Put it in question and answer session so that they can be taken up. Feedback link will be shared at the end of the question and answer session. This will help us to give you e-certificate as well as the copy of the presentation. And the link will be closed after 30 minutes. So thank you all. And without wasting further time, I would like to request Mark sir to start his session. So I'll make you a presenter.
That's great. Thanks for the wonderful introduction, Professor Shalar.
Thank you, sir.
This is the beauty of LinkedIn. Professor Shalar and I got connected on LinkedIn and had a number of conversations, and he invited me to participate in this session, and thank you very much for organizing it. This is very exciting, and I think it's an opportunity for building better collaboration in the power quality area. So I'm excited about that. All of the areas that you're working on, consultancy services for investigating problems and power quality monitoring and benchmarking, are obviously areas that we work on with utilities around the world as well. So should be some tremendous opportunities for collaboration. Let's see if I can share my PowerPoint and we can use that as a basis for discussion. Sharing Microsoft PowerPoint. Okay.
That presenter view is on.
Presenter view is on.
Yeah.
If I go to,
So Randy, top, go to slideshow. Home. Use slideshow. Yeah, second one. Yes, sir. It's visible now. Thank you.
okay, great. Use that. So we're the topic for today is, it's not a discussion of fundamentals in power quality, but I'll talk about research priorities for power quality. And I think with the audience of students and professors and industry folks, maybe this can generate some thoughts about research topics for thesis and for ongoing activities that can help move the whole world forward in the power quality area. So that was a great introduction by Professor Shalar. About myself, I go back about 40 years working in the power quality area. I worked for a company named McGraw-Edison that made equipment for the power system, from transformers to switchgear, fuses. And we ran a group called Systems Engineering that did power quality investigations and simulations of power quality phenomena, and developed software. Roger Dugan developed one of the first harmonic analysis software tools back at that time. And we've developed it further many times over the years. I've been always very active in standards in IEC and CGRE and IEEE. And standards are very important, and I think still a big need to continue work on power quality standards. And it's always been a focus since I joined EPRI in 2003. So for the last 17 years, I've been working at the Electric Power Research Institute. And we developed a strong power quality research program in cooperation with industry at EPRI, and that continues to this day. At EPRI, if you're not familiar with the Electric Power Research Institute, we are a collaborative research organization that is we get our funding to do research from electric utilities around the world. We're a nonprofit organization working on tools and technology to advance the whole electric power industry. So we have utilities working together from around the world. We have our regional representative, Paul Pickering, is on the call here today. So thanks for joining, Paul. We appreciate that. And we have a strong public benefit mission as part of our nonprofit status to work on participating with industry around the world to advance technology in the power system area. And it's more important than ever, as we'll talk about here, and goals around decarbonization and efficiency and electrification, that there's a lot of collaborative development to do to advance the state of the art and accomplish these decarbonization goals. So international coordination is very critical. As we've learned during the pandemic, especially when we have something like COVID-19 issues facing all electric utilities around the world at the same time, it's really illustrated the importance of sharing information, lessons learned, approaches for control center operation, for managing the workforce, or disinfection. And I think it's really helped keep the lights on around the world, this collaborative approach. So very exciting. It's worth, I'm going to put the research priorities for power quality in perspective with relationship to our work on the smart grid, or we like to call it the integrated grid. And there's a lot of challenges here as we work on integrating everything from the customer's adjustable speed drive or air conditioning, smart thermostat, or electric vehicle charger, all the way up to the operation of the bulk power systems and frequency control and market operation. So, and that integration is absolutely critical to accomplish the goals of integrating more and more renewables at the bulk system level, large wind and solar and hydro systems, with distributed resources all the way down to batteries and electric cars and control of smart loads, small PV systems on rooftops with smart inverters, and getting the flexibility that's required to make all of that work requires tremendous effort. And throughout all that, assuring that the quality of power delivered to each household, each commercial building, each industrial facility is at the level that's needed to make the equipment work properly. We call that compatibility. We'll talk about that. So power quality is critical, and it's more critical than ever as we have intermittent and variable generation on the distribution system, and we have control systems interacting with each other. We have weak systems because of low inertia and weak short circuit capacity. And all of these things contribute to the potential for power quality problems. All of those issues that Professor Shelar mentioned, harmonics, transients, voltage regulation, voltage sags that can cause equipment not to work properly, are all issues that can be magnified as we work on the integrated grid. So it's an exciting time to do this integration and have smart customers and get flexibility from distributed resources, but it's also a challenging time to maintain the quality of power required while we're doing all of that. So with that as a background, these are 8 research priorities that I will talk about. And I'll just say that go, Professor Shelar, go ahead and stop me if you see an appropriate question in the question and answer box, or if folks watching on YouTube are putting questions on the chat. Go ahead and stop me, and we'll address those and talk about those. It can be a little bit informal as we talk through this. But I think these are 8 potential priority areas, and we can have a discussion about each one of these and what some of the challenges are. Okay, so we don't need to go through the list right now because we'll go through each one at a time. And we'll start with monitoring, because at the fundamental level, if we can't characterize the issue, it's going to be hard to solve it. So we have to be able to describe the power quality issues, and we have to have data providing characteristics of the power quality issues. This helps us identify the cause. It helps us identify potential solutions, where the problems are. So monitoring is critical. Over the years, we've gone through probably a focus on monitoring for what I call benchmarking. So gathering data about voltage levels, voltage sag performance, harmonic levels, transient voltages, and characterizing the performance on the supply system, characterizing performance in customers' plants. And we call this benchmarking, and we have special purpose power quality monitors that can calculate all of the power quality parameters according to IEC 61000-4-30 standards for this power quality phenomena. So benchmarking is very important. It helps us understand the power quality at a specific location relative to other locations and relative to the requirements for equipment to work properly. So benchmarking is very important. As we have more and more monitors and it becomes that are easier to deploy around the system, we have the potential to collect data from more and more locations. Data management, communications to collect that data become very important issues. And I think the systems for collecting power quality data will only get larger. So data management and data analytics with potential applications of artificial intelligence and things like that will become very important. More and more, we're seeing the power quality monitoring be integrated with the actual operations of the grid. So very important functions like locating faults and diagnostics on equipment to determine whether it's operating properly can be determined from the power quality monitoring results in real time, and we can use that to actually manage and operate the grid or the local system better with an understanding of what's happening out there. So let's look at a couple examples. Going back to benchmarking, a lot of different ways to present benchmarking data for power quality. I just put a couple of examples out here. The one on the left is a way of describing voltage sag performance at all of the substations on a system. This happens to be a utility in Connecticut, and it describes the voltage sag performance. We use an index called SARFI, or the System Average RMS Variation Frequency Index. And so if we say SARFI 70, that means this is the number of times that a voltage sag went below 70% voltage at a particular location. And this chart illustrates the voltage sag performance over the last year, and then also has right next to it a bar that indicates the voltage sag performance over the last 3 years. So you can compare the last year to the last 3 years and see if it's getting better or worse. This is a utility that has relatively short feeders and low exposure to faults. So the voltage sag performance is very good. Voltage sags of, say, 4 to 10 voltage sags per year is very good. That's some of the best in the world. Then I also included what Power Grid in Singapore Power calls their SARFI map, and they have probably one of the best performances in the world. The system in Singapore is 100% underground and very low number of faults and almost no interruptions, but they still have some faults. And so their SARFI 70 is about 4.1 events per year. and over the whole system. And so that's still important because the industry in Singapore is a lot of semiconductor industry and industrial plants that are very sensitive to variations in the voltage. So if they get a voltage sag where the voltage goes below 70%, they could lose production of millions of dollars worth of semiconductor chips and have to scrap those chips. So power quality is an absolutely critical issue in Singapore, and they're one of the leaders in the world in researching power quality phenomena. And so, but it's interesting that they can provide this information for their industrial customers about how many voltage sags they can expect per year, depending on where they're located in Singapore. So a very interesting way to present results. And it's dependent on a power quality monitoring system that they have in Singapore, with power quality monitors all over the distribution system that are continuously recording these events. So those are benchmarking examples. As we integrate power quality monitoring with operations and use the power quality monitoring to identify problems and solve those problems, we can really increase the value of power quality monitoring. These are a couple examples that I always like to use. Yeah, of course, fault location is probably, the one application that's pays for itself almost immediately. Having monitoring even at the distribution substations that can help locate faults on the distribution system, and we can send crews out to repair issues that occur faster and send them right to the fault can be very valuable. But it's also possible to identify conditions that don't necessarily cause faults, but they could result in faults in the future. So we call these incipient faults or arcing conditions. In California and Australia, these arcing conditions can result in wildfires. So they're absolutely critical to be able to identify these exactly when they occur and solve the problem. Get rid of that vegetation that's causing the arcing, or that arrestor that's about to fail. And when it does fail, it could cause a fault that could cause a fire. So tremendous value in being able to identify from a waveform the potential causes of that disturbance. And that's a significant opportunity for artificial intelligence and data analytics to help with equipment diagnostics and fault detection and resilience and reliability improvement. The picture on the right is part of a voltage regulator that failed. That was an example of an event in Texas, and the waveforms next to it are the waveforms from the power quality monitoring at one of the customers that are served from that substation. And they noticed this voltage sag, very momentary voltage sag, and if you look at the monitoring at the substation current, you see that there was actually a short period where the current was interrupted. That straight line on that waveform, and that's that characteristic means that as the voltage regulator was going from one tap to another, it actually interrupted the current and then reinitiated the current very, very quickly. And that was happening over and over again. And arcing was occurring during those interruptions. And because of the power quality monitoring, they were able to find this problem before it caused the whole transformer to fail. So it was a very, very important, and say the value of the monitoring was paid for by saving that one transformer. So the point of the slide is that there's lots of research opportunity to understand the causes of power quality waveforms and from their characteristics, and increase the value of our power quality monitoring system. So we're going to continue to work on that. It's an area for a great opportunity for research and collaboration around the world. It's that's monitoring on the system side, but power quality is about compatibility. So the compatibility means that we need to supply the quality of voltage that's needed to make equipment work properly. And that's the bottom line. You know, some equipment can handle more voltage variations than other equipment, but the issue is, you know, to provide the level of quality that's needed, that customers' equipment can work properly. So to really understand that, we have to monitor at the customer. We have to understand the power quality, where the equipment is, and what the potential issues are there. So we look at this concept of compatibility. You may have seen curves like this one that illustrate power quality events. They are the red dots. You know, every dot represents a voltage sag or a voltage variation, and the lines represent the standards for compatibility with equipment. They represent the levels of voltage sags in terms of magnitude and duration that the equipment should be able to handle. So we like to say that, you know, we would like equipment to be able to operate properly, even if the voltage goes down to 70% for a half a second. So 70% voltage for a half a second, that allows a lot of events that are caused by faults on the transmission system or on parallel distribution systems to be handled. The equipment doesn't misoperate for those events. Of course, for a lot of voltage sags are below that, and we have to work on improving the performance for those voltage sags, or improve the ride-through characteristics of the equipment. So that's what compatibility is all about. But the point is we have to understand the power quality at the customer to be able to figure out what causes the equipment to have problems and what levels of power quality are okay for the equipment operation. As we look at the customers, the characteristics of customers are changing. And this is in a slide from a roadmap that we worked on with the utility in Arizona in the United States. And it illustrates their vision of the future grid. And this vision is becoming a reality very quickly, where instead of having the generation connected to the transmission grid and the distribution grid just supplying power to customers, now we have resources everywhere at individual customers, energy storage, photovoltaics. We have everyone sharing in the responsibility for resilience with local microgrids and backup power systems. We have smart communities and smart cities working together to optimize their energy systems and their resilience and reliability characteristics, and implementing new technologies like peer-to-peer energy sharing between customers within that city or that community. So lots of concepts that all need to be considered with respect to their power quality impacts. As the role of customers change and they have their own energy storage and they have their electric vehicle charger and they have photovoltaics on the roof, all of those things can impact their power quality characteristics as well. So this complexity of the customer, industrial, commercial, residential, needs to be taken into account when we're determining their power quality requirements and their power quality characteristics. I just mentioned a few smart communities. I think personally, this is an area that I think is one of the biggest changes and kind of basic level changes that we're seeing in power systems around the world, is the importance of the community. for managing their energy use, connecting energy systems together as we move towards hydrogen as an energy resource. You'll see the linkage between gas networks, which might become hydrogen networks, and the electric networks, combined heat and power systems for communities, local community photovoltaics, community storage, and intelligent and communications to make those systems work. So watch for these kinds of examples occurring around the world where intelligence at the community level is where energy management is part of that intelligence. And an opportunity for research is to make power quality management part of that community responsibility as well. So maintaining the required power quality for everyone in the community, voltage regulation, preventing faults that can cause interruptions and voltage sags, controlling transients within the community, all can become part of the community responsibility. So power quality as part of the smart community responsibility, another very important research. You'll see some papers, in CGRE talking about this as a research area in Europe right now, with the local energy communities is the term that they use. They use the term advanced energy communities a lot of times in the US. So I think this is a very important area as well. This, I wanted to include this concept just as an indication of where I think power quality is headed from a power quality monitoring point of view, from a data point of view, from an intelligence point of view in terms of diagnostics. And this is an illustration of a device that is called an energy management circuit breaker that we've had a research project working on for a couple of years with one of the manufacturers, a company called Eaton, that makes circuit breakers. And these are the circuit breakers that go in the house. This particular format, is a form factor that's used for circuit breaker panels for residential customers in the US. And so one of these circuit breakers might serve your water heater, or one of these circuit breakers might serve your air conditioner. One of these circuit breakers might be on your energy storage system or your PV system on your roof. And what Eaton has done is built a circuit breaker that has monitoring capability. So the circuit breaker can measure not only energy use, which it can measures energy use down to 1 second, so we can get 1 second energy data, but also triggers every time there's a disturbance. So when there's a waveform like the waveform shown there, that happens to be at my house in Tennessee, when I'm in Tennessee, I can watch it even when I'm here in Ireland. I can watch for disturbances at my house in Tennessee as well, and determine whether that voltage sag is enough to cause a problem with the equipment that's being monitored with that circuit breaker. So, and besides having monitoring for the energy use and disturbances, the circuit breaker also connects to the Wi-Fi in the house and has internet web services to go with it, so that we can continually have access to this data in real time. As soon as a disturbance like this occurs, I get a notification on my phone that there's been a disturbance, and then I can go take a look at it and see what the problem was. And just think about the data from every residential customer having multiple circuit breakers with power quality monitoring capability right in the panel of their home or their commercial building or their industrial plant. So that power quality monitoring becomes part of the quality of service for every customer. And built on top of this device, we can provide new services for the customer, or we can make it a community that manages these devices for all the customers within that community. And we can do equipment diagnostics with that device. So maybe there's a particular waveform characteristic that's an indication that the motor in your refrigerator needs to be replaced, or you need a new refrigerator, or the compressor on your air conditioner needs to be fixed or replaced. So equipment diagnostics with monitoring on every device that you want to monitor. And this monitoring could be actually in the devices themselves. And so this illustrates the concept that I call the integration of IoT devices, the Internet of Things, and power quality, taking advantage of low-cost sensors built into devices all over the grid. It's a huge data management challenge and a huge opportunity for data analytics and increased value. So the research opportunity here is just tremendous to create the value for platforms like this that have monitoring and control of individual circuits all over the grid. So I think that's a real example of this Internet of Things concept applied to power quality. So all of our knowledge about power quality can now be applied on a much broader basis with the availability of the monitoring data. It's exciting, isn't it? All right, so that's two. That's so monitoring and the customer. That's the first two. The rest of the 8 I'm going to go through a little bit quicker because really those were those set the stage, and you'll see that over and over again as we look at other priorities for power quality research. Let me just stop for just a second and ask Professor Shelar, do you have any comments or questions or thoughts, or are there any other questions that we should address from the question and answer?
Right now, there are no questions. Yeah, 1 minute. Yeah, Ramesh sir has written, Mark, low short circuit ratio, renewable energy connection to microgrid, challenges voltage, reactive power balance, harmonics. How do you tackle these problems to keep PQ intact? What are the new researches?
Yeah, okay, great question. And we're gonna low short circuit ratio systems is one of my items, so I'll wait till I get there for that. But managing the voltage and the reactive power on weak systems with variable generation, this is one of the challenges of the day. So we'll come to that and talk about that. I think that question has hit on one of the most important challenges in distribution system design today that we have to deal with. And this slide is actually one of the answers to that. One of the directions that we're headed, one of the trends is what I call power electronics everywhere. And obviously we see power electronics in photovoltaics on people on the rooftop or in communities. We see power electronics in energy storage devices. We see power electronics for electric vehicle charging. But I think we'll also see, we have talked for some time about power electronics in the transformer itself, and build either making power electronics based transformers or transformers that are hybrids and have kind of a conventional transformer with some portion of the transformer being able to be controlled with power electronics so that we can control the voltage and reactive power. One of the advantages of power electronics in these applications is they provide opportunities to manage the reactive power and the voltage. Most of these power electronic devices can be operated at different power factor levels, different reactive power levels. That's one of the standards for smart inverters for PV systems, is to take advantage of the reactive power management that's available from those inverters and make that part of the design of the distribution system. So new designs for the power electronics itself, as well as taking advantage of the power electronics that's out there from an integration point of view as part of our reactive power and voltage management, is very important research areas going forward. So that's all you power electronics people, big opportunities. One thing that comes up associated with all this power electronics is concerns around new frequencies that maybe weren't a concern before. Since most of this power electronics is being designed as pulse width modulated type of power electronics devices, so it has relatively good character. They usually have relatively good characteristics for our traditional harmonics at the third harmonic and the fifth harmonic and the seventh harmonic. They're controlled very well within the standards, but these devices have switching frequencies that might be 15 kilohertz or 20 kilohertz or even 50 kilohertz. And those switching frequencies can cause, we'll use the term in quotes, harmonics or noise on the system at those high switching frequencies and harmonics of those switching frequencies, and excite local resonances. We call this supraharmonics. That's kind of the new term for this. Harmonics that are in the 2 to 150 kilohertz range. A lot of research being done. You probably have heard the name Matt Bullen. Matt is a fellow researcher in Sweden that's been a leader in power quality standards and power quality concerns, and he comes up with a new book every couple of years. Matt is doing a lot of work around this topic of superharmonics right now, and some of his graduate students are publishing excellent work. So watch for this space and look for potential issues. Include communication interference, include local resonances and problems with power supplies in local devices in households and commercial facilities and industrial plants. And there's been cases with local resonances even causing local heating in transformers and transformer failures. So it's an interesting area that I think we're just starting to understand and figure out if we need some new standards to deal with it. Superharmonics. Question.
One minute, sir. Yeah, one question. Dr. Mahendra is asking why DOE is not focused on supraharmonics in bidirectional charges development.
Yeah, I think that's a good question, and I'm not with the Department of Energy, so I don't know the specific answer to that. But I think that we haven't seen that many problems that are attributable to superharmonics yet, so the concern has not really been raised to the high enough level yet. But I think we'll see this become an important issue as chargers, bidirectional chargers, and power electronics kind of throughout residential systems, and at locations at rest stops on highways and everything else, that where we end up seeing interaction between these devices and other power supplies. Could be a power supply for a computer, it could be a power supply for any other piece of electronic equipment. That's where we're seeing that the local resonances cause problems. So it's a good question. I don't know the answer, but watch for, there's a lot of work being done. DOE just put out awards for a whole range of new projects in the area of electric vehicles and charging systems and integration. And hopefully some of those researchers can work on the superharmonics area as well. Good, very good question. Okay, Sasha?
Yeah, he had just mentioned NLAAD was doing good work on this problem.
Very good. Very good. Keep that in the notes so that I can look that up. I would be interested myself in checking on that.
Okay.
Very good.
Okay, sir. Thank you, sir. No questions further.
So there's one question from From Dwivedi sir.
Okay, let
Uh,
me check it.
will the household gadgets current signature analysis become affordable in near future?
The answer is absolutely yes. That's that energy management circuit breaker. And I'm glad that question was raised because it illustrates the importance of the current. You know, all of our power quality benchmarking has been around measuring voltages and characterizing voltage because that's the quality of power that we deliver as a utility to the customer is in the voltage. But all of the information about something going wrong or a fault condition or a problem with a piece of equipment, all of the good information that contains the characteristics of the disturbance are in the current. So having measurements of the current and current disturbances and building databases of those current characteristics along with the results that were associated with that current, the equipment involved and the condition involved, building those libraries of data so that we can apply analytics and artificial intelligence. That's such a huge opportunity, and it's very important that the monitoring include the current. And devices like that energy management circuit breaker that are measuring voltage and current all of the time at individual equipment, and at a relatively low cost because the communication system is already there with the internet and your Wi-Fi, the device and its sensors. You need to have a circuit breaker there anyway. You know, for instance, that energy management circuit breaker, probably right now it's still a little bit expensive. I think it's about $300, but it will be a conventional circuit breaker costs about $40. That circuit breaker will be about $75. So you'll be able to see where the cost for the monitoring will be worth the money because of the value that you'll be able to get in terms of equipment diagnostics and energy management. And a lot of that comes from the monitoring and the current.
Okay, sir.
All right. And we did want to talk about low short circuit ratio systems. We had a question about this. This is kind of the ultimate challenge as we get more power electronics and we get more local generation, and the need for conventional rotating machines providing generation becomes less. Then we get systems that have lower short circuit capacity. The characteristics of those systems are that if we have a fault or even a load variation, managing the voltage becomes more difficult because a load change has a bigger impact on the voltage. Faults have an impact over larger areas of the system. And where this becomes particularly important now is in microgrids, where when a microgrid goes from connected to a grid which might have a higher short circuit capacity and goes on its local system where the generation might be PV and batteries, and maybe a fuel cell, then that's we have to change the way we do protection. We have to make sure that the power electronics for those PV systems and energy storage systems and fuel cells can manage the voltage accordingly, including managing the voltage when there's load variations. So these challenges are research topics that are being studied all over the world, is using the power electronics to make sure that the power quality is adequate, even for low short circuit ratio systems. And even to the extent of making energy storage and other systems look like inertia, so that as for systems that need inertia, if we can get that inertia, we call it virtual inertia or artificial inertia from power electronics and energy storage systems, then that can take the place of rotating machinery on large systems. So it's very important to understand the impact of low short circuit ratio systems, how we can deal with those systems using the control characteristics of power electronic devices. And of course, this is a challenge because those power electronic devices might be distributed throughout the system, and we have to make them work together. It might not be just one energy storage system or one large PV system like you see on the bottom right there, where that photovoltaic plant is providing the backup power for that whole community at the top right. That so you can build the smarts into the power electronics for that large PV system, but it might be PV that's on rooftops of all the houses instead, where we have to make those work together. So coordinated control through power electronics becomes the solution to some of these low short circuit ratio problems that we have to work on from a research point of view. Okay? And some of those problems that we have to work on, voltage regulation is right at the top with these low short circuit ratio systems and distributed resources like PV systems that are intermittent and clouds go over, and we have to maintain the voltage during those disturbances. We have to be able to deal with reverse power flows. We have our traditional ways of controlling the voltage using voltage regulators and capacitors, but maybe that we have to make sure that can work in conjunction with the voltage control functions of the power electronic devices themselves, or the smart inverters. We may need, the smart inverters may not be enough. We may need to take advantage of energy storage devices, which can provide real power for control of the voltage. And as the penetration of electric vehicles gets greater and greater, we have to really look at the impact of larger numbers of electric vehicles and the opportunity to use that electric vehicle charging as a flexibility resource as well. So a lot of research topics around managing distributed resources locally and with what we call a DERMS, a distributed energy resource management system, and building power quality management into those systems. Does that make sense?
Yes, sir.
All of these things require models. And we continue to work on modeling approaches for harmonics and transients and voltage regulation and fault analysis. And these models have to be built using our distribution planning models, taking advantage of our geographic information systems, knowledge about the characteristics of the devices on the system, the transformers and capacitors and regulators. And now we have to include in these models all of these controls for energy storage devices and smart inverters, and be able to model the interaction of those controls. Very important. The frequency response characteristics of the system is changing, and we have to be able to model the way that customers' loads impact that frequency response. We have to be able to model the impact of power electronic devices on that frequency response. It's very complicated. It's a difficult problem. Some of our traditional tools that just rely on linear system modeling and admittance matrix solutions can't model the characteristics of these power supplies and power electronic devices adequately, so we have to get approximations for that. More and more of the system is being put underground for reliability and resiliency, and that changes the frequency response, changes the resonances. So that's a very important characteristic we have to understand in the models. We talked about superharmonics. The models for system at 50 kilohertz are very different than the models for a system at 300 hertz or 60 hertz or 50 hertz. So we have to be able to look at how to model local systems and local resonances to study some of these high frequency characteristics. And finally, we have to be able to model microgrids and the interactions that occur within a local energy system from a power quality point of view. So there will be a lot of continued research work in the area of system models and modeling requirements. And this is an area for tremendous potential collaboration around how to do this modeling and the tools. EPRI is a big fan of open source software. Would be very interested in looking at we have our OpenDSS distribution system simulation software. That software was developed for power quality analysis as well as traditional voltage analysis and distribution planning. You can use that modeling software to do frequency response analysis and harmonic analysis in general. It's not a transient analysis tool, but there's open tools that are available for transient analysis like EMTP as well. So the tools are out there to collaboratively work on advanced models for power quality analysis, and we look forward to that cooperation.
Yeah, one related question, sir, from Narendra Dwivedi. Sir, models for multiple non-linear loads connected to a single bus and their analysis for time of the day with varying loads is not readily available. I think he is giving some comment on that.
Yeah, that's been, that's a kind of a traditional problem in harmonic analysis is, representing hundreds and thousands of devices that can produce harmonics, and they're all operating in a statistically different way. So, they're not all producing the maximum harmonics at the same time. And how do we study this from a simulation and a planning point of view, all the way from worst case analysis, assuming that all the devices are producing harmonics at the same time, and are they producing harmonics that are in phase with each other, or do they cancel each other? And these are important characteristics. The tools are available to do that. It's not OpenDSS for harmonic analysis. You can simulate thousands of devices producing harmonics. We do that for distribution studies all the time. But and so that's not a problem to represent what's happening. The problem is to know what cases to study. What cases, how do we model the variations in the phase angle characteristics of the harmonics that are produced by those nonlinear devices and relation to each other, and what are realistic cases and what are not realistic cases. So there is a lot of work still to be done to understand the interaction between lots of devices, whether they're connected to the same bus or they're connected all over the distribution system. It's the same concern, but the tools exist. So the opportunity to do the research and create the projects using those tools is exciting. So there's opportunity to work together. And if you're not familiar with how to use OpenDSS for example, for a study like that, we can point you to example cases that are part of the material that you can download from the SourceForge site where the software is. There's example cases for many of those types of simulations.
Yeah, thank you, sir. One more related question from Rajan Mehta. Is the Open PQ database project still ongoing, where PQ event data were being put for the research of the community at large?
Yeah, that's another very good question. We had a project with the Department of Energy that where we built a large database of disturbances and power quality waveform characteristics, and we haven't added to that power quality database in a number of years. So it's not active right at the moment, but it is a topic that we are talking about reinvigorating and creating a collaboration, because I think there's tremendous opportunity there. So I'll take that as a request to get that started and expanding again. That database is probably 10 years old now, and it still exists. And I can get a link to it so you can access that open database that was built for the Department of Energy. But I think there's an opportunity with monitoring at individual buildings and stuff to really increase the data that's available to enable analytics applications to be developed all around the world.
Okay, sir. Thank you. He has mentioned that, yes, sir, that would be a great assistant to the PQ community at large. Thank you,
Great.
sir. There are a few questions, but they are not related to this slide. Some related to Harmonix. We'll take it later on.
Yeah, we'll get them at the end. So this is the kind of the last topic that I wanted to address, and it's probably the most important in the end, and that is, power quality is about compatibility, and the ultimate compatibility is the economic impacts. If equipment doesn't work properly, but it's very easy to restart and it doesn't have much of an impact cost-wise, then that's not so much of a problem. We just restart it and go. But if it causes the equipment to fail, and that's a very expensive problem, then that's much more important. So in the end, power quality issues are economic issues. And that means that the economics of power quality is about where do we spend the money to improve the power quality to get the optimum answer, and how much should we spend? So we have power quality impacts on equipment, but we have expenses to improve power quality. So we have to balance those two things with respect to each other, and we have to look at where the best place is to spend the money. Do we improve the power quality ride-through characteristics of an individual controller by protecting that controller because it's the weak link and then everything else works okay? Or do we spend a lot of money on the grid to prevent faults from occurring and then eliminate the voltage sag from occurring in the first place? So we like to be able to characterize the performance, as we described all the way back in the beginning when we were talking about monitoring power quality, by publishing that SARFI map that they published in Singapore, and industrial customers understanding that they can expect 4 voltage sags per year where the voltage is going to go below 70%. And if even 1 voltage sag is enough to cause them millions of dollars of impact in their semiconductor process, then it's going to be worthwhile for them to protect their process. So the solution for that very sensitive customer with very costly impacts is going to be to figure out where to make my process work better by working in the plant. If the number of voltage sags per year was 40, then maybe the utility should be, spending money to reduce the number of faults. And one of the traditional kind of power quality compatibility cases that always comes up is like a plastics plant. Plastics plants are sensitive to voltage sags, and voltage sag that goes below 70% may cause a lot of the extruders in a plastics plant to trip offline, and it makes a mess because there's plastic all over the place. And then we have to restart all those extruders, and that has an impact of lost production for all that plastic bags or plastic film or whatever is being produced. But maybe there's a limit to how much the utility can spend to improve performance, and it might be expensive for the customer to protect the equipment as well. And it's, in the end, plastic's not that expensive, so you might have to live with a certain number of events per year, and because it's too expensive to fix the problem. But if there's too many events, then it's worth spending the money to fix the problem. But in the end, it's an economic problem. How much is it costing? How much does it cost to fix it? And, where's the optimum place to fix it? So a lot of those studies that Professor Shelar described on the very first slide that they work on are about going inside a plant, working on their process, figuring out how to make it work with the quality of power being delivered, and work with the utility to improve that power quality to the extent possible, and finding the best economic solution for improving performance. And in the end, that's what power quality is about, is achieving the most economical solution to get the compatibility that's required. And so economics is important. There's some good CGRE reference documents that describe this. There's IEEE standard as well that describe this economic analysis procedure. And it's very important to understand, because theoretical solutions need to turn into economic solutions. And I'll finish up just by mentioning standards. We need to continue to work on standards. The IEC and CGRE working groups continue very actively in this area. There's a whole group of IEEE standards on harmonics and voltage segs and power quality improvement. And this is a diagram that we developed a number of years ago that just illustrates how these standards interface with each other. It starts with compatibility levels and understanding the expected performance. Then on the system side, we can work on achieving that performance. And on the customer side, we can work on making sure that our equipment works properly based on those compatibility levels. And of course, we have measurements, monitoring systems, evaluation procedures that go between those customer systems and the supply systems to help us understand the issues that come up and the solutions to those issues. And there's important standards in all of these areas as we work towards achieving this compatibility concept. So plenty of work to be done, because as we work on this integrated grid, the requirements keep changing. So we need to keep revisiting all of these issues again. So with that, we'll open it up for any additional comments. And thanks for the advertisement for our book. Roger Dugan deserves most of the credit for this book, but it is, and Surya Santoso, who's a professor at the University of Texas, has been carrying the ball on this book for the last couple issues in terms of doing a lot of the work to update it with the latest issues. So thanks for that. And maybe we can have some questions.
Yes, sir. Thanks a lot. I'll take a question one by one. One minute, sir. I'm taking question. Yeah, Narendra Dwivedi sir had asked, sir, do you feel sub-cycle disturbances do not affect gadgets with SMPS at front end if SMPS has adequate capacitor filtering?
Could I get that again? I understand the sub-cycle filter is affecting, but what kind of devices are we talking about?
Any gadget with SMPS. He's saying that there are many gadgets with SMPS now at front end, and if SMPS has adequate capacitor filtering, will it be having any problem in sub-cycle disturbances?
Yeah. I think that there's concerns, sub-cycle disturbances, transients, Superharmonix. This is an area where devices where the filtering for transients, to protect those devices might actually cause them to be impacted by 2 kilohertz or 10 kilohertz, switching components from other devices in the same facility. So interaction between devices at these high frequencies can be impacted by the filtering characteristics in those individual devices and their power supply characteristics. So I think there's still that's a changing area that affects the design requirements for individual devices and their performance, both as a producer of disturbances as well as being impacted by disturbances.
Okay, sir. Narendra sir, if you want to discuss, you please raise your hand. I will also unmute you. Next, I will take a comment from Martin. He has written a comment on Superharmonix. We are facing a lot of Superharmonix in area 4 kilohertz, and its harmonics caused by insufficient earth concept of VFD. So switching frequency and its harmonics of drive transfer to mains may be a topic to add to the presentation. He has given a comment.
Yeah, very good. So you're saying that the superharmonics are caused by adjustable speed drive power electronics? And those larger devices, having switching frequencies around in that's the lower end of the superharmonics, the 2 kilohertz and 4 kilohertz. But the larger the device, the more likely that the switching frequencies are in that lower range. So it could be very important. Thank you very much for that.
Yes, thank you, sir. Then next, Rahul More is asking, how much will energy storage impact power quality?
I think energy storage, is an opportunity, and a concern, because obviously more power electronics, creates some power quality concerns. But for the most part, energy storage is a potential stabilizing resource for the voltage in general that can help us actually during voltage sags, but also especially during normal voltage variations and reactive power requirements on the grid, besides being a source for resiliency and reliability. So most of the impacts of energy storage are on the positive side for power quality. We have to watch some of these things in terms of higher frequency interactions and concerns like that, because it can be high power devices. But those are the design challenges that we have. In general, energy storage is an exciting opportunity to make the whole system work better.
Sir, there's one.
Yeah. So, madam,
Sir,
go ahead.
there's one question by Dr. Mahendra. Why IEEE 1159 has inrush current transient as PQ problem?
The inrush current, both for a motor or for a transformer, it has the potential of causing voltage sags just like faults. So, depending on the strength of the system, a very large motor or a very large transformer, the inrush characteristics, well, for a motor, it's mostly a voltage sag concern, and making sure that the system is strong enough to start that motor without causing voltage sags that can impact other customers. So that's one requirement. For a transformer, there's two concerns. One is during the inrush to a transformer, the current is full of harmonics that are not usually there. So we have even harmonics in the second harmonic and the fourth harmonic. So all of our traditional harmonic analysis comes into play for transformer inrush current. So for the most part, in 1159, in that particular standard, we're talking about the voltage sag concern. But you also need to consider in your harmonic analysis the inrush to transformers, in particular because you might design filters to solve harmonic problems with your traditional loads like adjustable speed drives, and those filters might cause a resonance at the fourth harmonic. And then you think, okay, we don't have any fourth harmonic. But when you energize transformers, that inrush current does have fourth harmonic, so you can excite a resonance that you've created by doing your filtering for other loads. So for both of those reasons, it's important to consider inrush characteristics as a power quality concern.
Okay, thank you, sir. Actually, there is one specific question. I'll ask that. It's a big question from Sitaram Murthy. A solar plant installed in an industry is set for 100% active power generating. The industry load requirement of reactive power is not met by solar PV and it is importing from grid, thereby increasing the import of apparent energy. The fifth harmonic is predominant around 70 to 80% of fundamental. How do we mitigate this?
I think there's two questions there. One is the harmonic question, and one is the kind of a more conventional reactive power question. I think you see the requirements for inverters on PV systems have been changing, at least in the United States, to where inverters are being required to have some capacity to provide reactive power support as part of a voltage regulation function, in addition to their active power capabilities. So even at full power or full PV system active power capability, inverters, at least above a certain size, I think like 100 kilowatts or something, so not necessarily a requirement for a rooftop, but for any large PV system, the inverters in most places, and it's kind of a state-by-state thing in the US, are required to be able to provide reactive power and voltage support according to requirements in the latest IEEE 1547 standard, which defines some of the inverter characteristics, the control functions that could be implemented. That those control functions that are defined in IEEE 1547 are starting to be included into requirements for the inverters as part of interconnection for a lot of PV installations. So your comment is completely correct. It's very important that PV systems and inverters be an active participant in managing the quality of power on the grid. And I think we're making some progress in those requirements in many places in the world. You see it in Germany, you see it in the US, and I think we'll see it everywhere, as we get comfortable with it.
Yes, sir. I think, and for harmonics, I think they need to install harmonic filters after the proper power quality monitoring.
And harmonics, if the PV inverter should not be the cause of fifth harmonic problems. That would be, most of the PV inverters are PWM type of inverters that don't produce only very low levels of fifth harmonic. So if it's a very inexpensive inverter that has significant fifth harmonic production, that would be a concern. You could solve it with filters, but really should be a better inverter than that.
Okay, sir. Thanks a lot. Next question, Subodh Bide. What are the area for research to maintain the stability of systems flooded with such large different generation sources, particularly solar plant, which are very unstable?
Yeah. I don't know if they're unstable, but they are variable and they are intermittent, so they come and go, and that can cause voltage variation problems. They can cause different reactions with those voltage variations can impact other loads and other generation sources on the system. I think the main concern and the challenge that we have is control system interaction. The thing that we don't understand is we are going to ask these large PV systems and energy storage systems and electric vehicle chargers to be active control devices with control functions. and maybe participate in voltage control and things like that. And we haven't built the tools to really understand how those control systems could interact with each other. And there is a possibility that those control interactions could be instability. I think a PV inverter control for a local PV system is not inherently unstable. There's not really a lot of stability concerns associated with that. But when you combine that with a large energy storage system and other large fast charging electric vehicle systems that operate, with variable loads, then all of those control systems interacting is something that we have to study.
Okay, sir. There are two participants who would like to talk to you directly. Can I unmute? Yeah, Rajan sir, you are unmuted now. Okay, you can talk.
Thank you very much, sir. Hi, Mark. I had a question specifically around SAG occurrences. So the background is this, that typically EN 50160 or such standards, they have the SAG compliance on an annual basis. Like as you mentioned, the SARPI indexes that you mentioned, the SARPI intensity, is providing the number of SAGs over a period of year that the utility has to adhere to. Now, the case where in India, for example, almost most of the utilities, they do not have any SAG information or annual SAG data available. So when we are talking about doing studies for, say, facilities, specifically, say, like the one Mr. Shelar mentioned, we go inside a facility and we are doing, we are trying to diagnose problems, or we just want to find out what is typical SAG occurrences which they need to be aware of. So what is an optimum duration you would recommend that can be taken up so that it can be extrapolated and given as information to the utility company saying that, hey, look, we did for a week, the SAG intensity looks so and so, although we do not have an annual SAG occurrence data, but this is something that can be reasonably taken up as valid information for you to act on. Does that?
Yeah, that's a very good question, and it's a tough one because the voltage SAG performance is dependent on faults, fault performance, how many faults occur on the supply system. And faults don't occur that often, and they may be very different in different times of the year for different causes, if there's a rainy season, or if there's a storming season, or if there's a fire season. So in general, at least 6 months or a whole year, depending on how much variability there is between seasons, is needed to get any good idea of voltage SAG performance. And even a year, it changes from year to year. So it is a very difficult problem. So you also need to try to find other ways to estimate how many voltage SAGs could be occurring. And one way to do that is if you can find some data about fault performance, how many, we use a term called faults per feeder mile. There might be some data from the utilities about number of faults that occur on the distribution system because they have a count of the number of times protective devices operated or something like that. So you can take and translate fault data into voltage SAG data that gives you some idea of the performance that is expected at a particular location, but nothing completely takes the place of monitoring, and that is a challenge when it's not available. So keep the monitor there, and obviously if you monitor for a month and you see a whole bunch of voltage SAGs, then you already have enough data to say that you need to fix a problem. So, monitoring and starting to learn as much as you can, as quickly as you can, is going to be important. But if you're talking about a facility that is impacted by, 10 voltage SAGs a year, and you monitor for 2 months and you don't see anything, it doesn't mean it's not a problem. it still probably is a problem. You just haven't seen it yet, or you haven't hit the rainy season, or whatever. So both fault performance, use that in combination with system models to try to convert that to voltage sag performance. We call that area of vulnerability analysis, or keep monitoring for longer periods. There's no simple solution.
Thank you, Mark. Thanks very much.
Yeah, thank you, sir. Thank you, Rajan, sir. I will unmute Narendra Duvedi, sir.
Yeah.
Sir, you can talk.
Yeah. Good afternoon, everybody. I just wanted to share some information. As per latest CA modifications, now we can expect power quality recording at all bulk consumers as well as major tap-off points of utilities, because it has come into CA regulation and states are in the process to convert that. So maybe 2 years down the line, we might have a recorded SAG data available with the values as well as occurrences, and that can help Indian community research going on that. So it's a good news, but it will take some time. It will take about 2 to 3 years more to get it implemented all over India. The second thing which I just wanted to share was regarding that harmonics and solar PV. Now, the best solution, according to my experience, for that kind of a problem is correct power quality at load end itself in the plant, rather than drawing not power quality, reactive power. Correct it at the load itself. So grid will always look at load as if it's a unity power factor load, even if you are working on grid or on PV or a mix of both. So that, according to my experience, reduces drawing of harmonics to a large extent from grid when you are working on solar power. So no question of drawing more harmonics from grid under working with PV. This is implemented. Thank you.
Yeah, there's two very important comments there. Very exciting to see that power quality monitoring will be available kind of around the entire grid. And hopefully we use the 61,000-4-30 kind of specifications to get the same way of characterizing power quality at all those locations. That would be great.
Same meter specifications are there in the order now. So same.
Yeah. So Class A analyzer they have specified,
yeah.
And IEC 61000-4-30.
Yeah,
CEA is Central Electricity Authority. For Indian context, it's the highest authority, and
very
they have
exciting.
taken it. Yes, sir. Thank you, Narendra, sir.
Great comments. And a comment about the harmonics and reactive power. I think it's worth just emphasizing that, you know, almost all harmonic problems are associated with resonance problems. And resonance problems are usually associated with capacitors for voltage management and reactive power compensation. So you always have to be careful when you're doing reactive power management with capacitors that you don't create harmonic problems.
Yeah,
Resonances are way more important than this actual source of harmonic associated with the resonance.
Yeah, sir, I would like to add here, in my state, Maharashtra, KVAH billing has started. So there is a very rush for reactive power management, and there is always debate whether to use capacitors or active harmonic filters. So I wanted your comment. Will capacitor become extinct after some time and only active harmonic filter, or how do you see it?
Yeah. Well, I always think it's relatively safe to do reactive power compensation with filters. So, you know, instead of using capacitors, just tune it to 4.7 or something and put the reactive compensation in, you know, tune it below the fifth somewhere. And it's a very safe way to do reactive power compensation in general, and doesn't usually cause other problems, even though I mentioned that, you know, when you energize transformers, you need to be careful. But the in general, that's safe. But the more power electronic devices we have, the more opportunity we have to use those for reactive power management. Energy storage, PV systems, in the long run, should make the use of capacitors less necessary. because we can get the reactive power from those power electronic devices and use them like, I won't say active filters, that's another advantage, but at least active reactive power management. And without using capacitors.
Yeah,
So
okay.
the balance between using power electronics to control reactive power and using capacitors is changing, I think.
Okay. And even, everybody is in Maharashtra is rushing for unity power factor because, you get advantage in electricity bill. What is your opinion, unity power factor?
Yeah, I don't have any particular, I don't think it's unity power factor has any particular advantage in and of itself. As a matter of fact, PV inverters, having them operate at slightly lagging power factor is a good thing in terms of compensating for the voltage rise that's caused when they're in their maximum active power generation. If they can absorb some reactive power at the same time, it helps manage the voltage better. So it's actually better not to be at unity power factor in that case. So I think that, and it's losses and voltage control need to be analyzed, and whatever power factor is appropriate to manage the losses and losses and voltage in the best way, is the power factor that you need. So it may be that you need a lousy power factor somewhere in the grid to compensate for what's going on in another part of the grid, to generate the reactive power that's needed. So it's a system problem, and our tools need to be able to address it as a system problem. It probably become part of the, really smart requirements of a DERMS, of a distributed energy resource management system, is to manage the reactive power and voltage to control the voltage and minimize the losses. And it's not going to be as simple as saying we need unity power factor. That simple answer is not the answer.
Okay, so yes, sir.
It's not even a short-term answer. It's not even a short-term answer.
Yeah. Still, there are many questions. Can I take 2-3 more?
Let's do 2 more.
Okay, sir. Yeah, one question from my associate, Sujata Povnikar. What are the various softwares used at EPRI?
We use many commercial softwares at the transmission level, PSSE, we use EMTP, we use PSCAD. With a lot of our members, we use real-time simulation systems like RTDS. For distribution system analysis, we use SIME, we use a software called Synergy, we use a software called DigSilent from Germany. We have OpenDSS we use for a lot of our research tools, and we continue to develop on OpenDSS for additional tools, additional simulation capabilities. We use energy analysis tools and economic tools like Homer for buildings and local systems. We use a lot of regular commercial tools that are out there, as well as our own tools.
Yeah, thank you, sir. And now last question I will take from Anil Kumar. Although there are questions remaining, but we'll try to answer them afterwards in email. Anil Kumar is asking, can you please explain how to determine the harmonic power flow in a network and how effectively the concept of phase angle measurement can be used?
That's a whole course in and of itself, but it's a great question and one that is a topic of great discussion. Phase angles for harmonics are important in terms of the cancellation of harmonics between different sources as they flow around the grid. So it's an important concept to understand and include in the simulations. Tools are available to solve for the flow of harmonics around a grid, which is called a harmonic power flow, or at every harmonic, there's real and reactive power as well, and phase angles, and tools like OpenDSS and Matt Grady at Purdue University developed a tool called HarmFlow that uses a more traditional power flow solution method for harmonics. Tools that we've used and developed in the past use an admittance matrix solution technique at each frequency to solve for the flow of harmonics around the grid. OpenDSS uses that approach so that you can solve. So you need to know the magnitude and angle characteristics of the harmonics that are generated at all the sources of harmonics around the system in relation to the fundamental frequency sources in order to do a flow like that. So it's very complicated and difficult to get right. So we end up doing it more as a statistical analysis and assume that we can't get it right because it's changing all the time. Can be, so what it is at any moment in time could be different than what it is 10 minutes later in terms of the phase angles, harmonics, depending on individual load characteristics and the device characteristics. So it's a lot of the analysis, rather than trying to get the harmonic flows right at a particular condition and harmonic sources, it's to look at the whole range of possible characteristics for all the sources and do it from a very statistical analysis point of view. I don't know if that answered it, but we could make harmonic power flows the topic of a future webinar like this. And in that case, we got to get Roger to join us.
Yeah, thank you very much, sir. I can't thank you enough for giving such a long time and giving such a wonderful information. Now I would like to request our principal, sir, Dr. P.B. Mane, to say a few words. He has joined the session. Welcome, sir.
Yeah, thank you, Shalar, sir. A very good evening to all the participants, and I was not there to sorry for that, but I said that I'll surely join the session. I joined the session halfway, and surely on behalf of our institute and the management, in fact, we are very much obliged that you could spare your valuable time and guide all the aspirants and the experts who are working in this field of power quality. Indeed, the session was very fruitful, I feel. You gave the insights of power quality, and the number of questions which were raised in itself shows that.
Yes, sir. Yes, sir. Am I audible?
Yes, madam. Please go ahead.
Yes. Good evening, all. On behalf of All India Shri Shivaji Memorial Society's Institute of Information Technology, I, Mrs. Ashpana Shirarkar, Head of Electrical Engineering Department, would like to thank Mark Granahan sir for accepting our invitation, sparing valuable time, and delivering knowledgeable talk on power quality and integrated grid. Sir, your talk definitely thrown some light on some of the most important issues such as harmonic resonance, harmonics from power electronics, voltage regulation with disturbed resources, and superharmonics. Definitely, we will work for shaping the future of electricity. Thank you, sir. I must thank Sachin Shelar, sir, our PQ cell in charge, for his efforts in arranging this expert talk. I would also like to thank all the participants for attending this webinar and making it successful. Thank you, one and all.
Thank you very much. Thank you very much. And thanks for everyone with the great questions. I really appreciate that. Made the session much more interesting for me and makes me even more excited about working together.
Yeah, thank you very much, Mark sir. I'm really indebted to you for giving time to us. And, I'm also thankful to LinkedIn. We could connect and here we are after, I remember for last 1 year, we were trying to contact, and this is the COVID area has helped us maybe in a different term to get connected and be with you. Thank you very much, sir.
Great.
Yeah. Thanks, sir.
Have a great evening, and I look forward to the next steps. Bye-bye, everyone.
Bye, sir. Thank you.
जसं फीडबॅक लिंक इथे नाही टाकली ना.
I have put it in chat. Again, I will put.
Yeah, it is not visible. Many are asking for the link.
No, I have put it. Again, I have put it. You know, there are many.
Even it's not visible to me also.
I have put it to all attendees.
Okay. I was otherwise going to. Yeah, got it.
Yeah, thanks for that.
Hello, Shelar sir. Hello.
Yes,
Hello.
yes, ma'am. Yes, ma'am, you're audible.
हा शेलार सरांना नाही ऐकू जाते का? हॅलो.
Yes,
He's
madam.
on
Yes,
mute.
madam. I am trying to put the feedback link. There are some queries.
Okay.
There was some problem with feedback link. I have corrected it. Sorry for that. I have again put the same link. Please try it. But I have extended. I have again opened it, and it will be open for next 30 minutes. I have put the feedback link in the chat section. I hope it is available. Sorry, between I have reopened.